I want to start off with a very simple thing, right? First of all, in this whole area of data center, right? What has happened is a conventional processing, which was, a compute data center, was focused on, let's say, typical, addressing needs for, let's say, compute infrastructure for an enterprise like a bank. But now with AI, the big change that has happened is that the move to parallelism. Parallelism means instead of doing things sequentially in a very CPU centric architecture, we're moving to a GPU centric architecture where in parallel in 1024 cores of a GPU, we are sending the same computation to be done parallelly. So what the advantage you're getting? We're getting the fact that one in a sequential time, which would take 1,000 cycles, would get done in one cycle. So that is the power of AI, right? So power of AI is in getting to utilize maximum of the GPU. And because of this computational nature of exploiting the parallel architecture of the multi-cores, right? What happens is that puts pressure on the data center, because earlier, if you look at a CPU enabled workload where there was not that much computation being done overall, where there was one CPU or at most four GPUs, but now you have 1,000 processors working together. So the average heat that is generated, right, that is way higher. So if you look at, in fact, empirical studies have shown in comparison of AI data center versus a conventional data center for typical compute workloads, they have been shown anywhere between 50 to 100x kind of heat generation. So naturally, AI data centers have asked for more and more, innovative approaches to provide the required cooling. So naturally, AI data centers have not been, having sufficiently cooling environment with using just air-based cooling, etc. So they are used to, very complex liquid-based cooling infrastructure. So having said that, there is one concept which is again picked up from the software side, right? In software, what we found is, in general, when you leave the workload to be done by CPUs themselves, it is found that the typical workload, if you provision for peak capacity, let's say, for example, you're building an e-commerce site and you're building a provision for 1,000 users which is coming on Diwali site, so remaining time all the 1,000 will not be used. It's only going to be used 20 to 30% of the time. That means there's 70% not utilization of the or workload. And that is exactly what is happening in case of data center also, because the peak workload, when you're actually training the whole algorithm of the crunching of, say, the LLM transformer processing, which is happening, peak heat is required. If you provision the data center for that heat capacity required for the peak, the problem is that is where you have a issue, because you'll waste a lot of resources in terms of the heating. So that is where the concept of using AI to heat, AI to optimize the energy requirement has come up. So several domains it can be used. Like, for example, a very simple thing, like, just look at this. If you, instead of using the peak level load heat to be all through, if you can, do some kind of an optimization by saying that I will pre-cool the chips, pre-cool the data center racks before, the peak load starts to hit, it can save a lot of heating. At the same time, one more important thing you got to understand is, it's not about just heating a single, unit like a chip or the motherboard, but it's also about the whole server room, the whole data center. It is not that we will, again, the same principle, right? If you use a peak capacity of cooling required for the entire room, it's not the same. It may be that some part of the room may be requiring less heat versus what is required in some other parts of the room, more cooling is required. So if you can use AI powered with sensors, today sensors are there in every part of the data center, right in HVACs, right in the cooling equipment, right in the compute infrastructure of the data center. Using all of that, if you can optimize, saying that, okay, this part requires high cooling, so I'll run a high chiller, whereas the other part which does not require high chilling, I mean, even switch off the chiller. And another extreme of that, it is, in case it is possible that I know that ambient temperature is pretty good. For example, if you are running a data center in cold area, like, for example, something what's happening in, let's say, Scandinavia or somewhere where it's cold environment. Why don't you even, in fact, switch off the, what is called as the air conditioning, etc., and let the ambient air come in and substitute the requirement. So idea is, if you can use AI powered with data from sensors. So as I said, the problem you're solving can be a predictive, like for example, predicting where it is most likely to get more heated. So you may try to use the predictive model to pump more, cooling there, and then you can have predict prescriptive, which is optimizing the whole allocation of which resource to provide where. That is more like a prescriptive application of AI. So combining both predictive and prescriptive applications of I think we can really save. In fact, the interesting thing is, eat your own dog food, right? That's what is a mantra used in any industry. So Google, right, DeepMind, what they've done is they've used actually AI in their DeepMind data centers, and they've reported up to 40% savings in the energy cost. In fact, what gives that gives us a huge opportunity. What happens is that also helps them in, getting some carbon credits, which they can go and utilize. So overall, I'm saying is, instead of provisioning for peak loads, which is the conventional approach, if you can use AI itself by combining all the data coming from different sensors and combine predictive and prescriptive kind of analytics, you can really provide an optimal, energy scenarios. At the same time, there is also the other aspect of, if you let the heat outside from the data center, can you use it for other purposes, like for example, using it in cooling city swimming pools, or cool it in, add it to the, heating environment required for the urban infrastructure cooling equipment. That's another bonus. So I think overall, instead of staying looking at static models for peak cooling requirement, which has been the conventional approach, replace it with adaptive approach, which is based on powered by AI, targeted cooling to targeted locations and targeted to targeted workloads. I think we can have an order of magnitude difference, including up to 40 to 50% savings in the overall, consumption. And that's where the whole idea comes up, right? Because AI workloads require high heat, there's no doubt. But if you can use it again, AI itself, to help you in optimizing the heat requirement, that's a win-win. That's all I would like to say.